Welcome to Lesson 10b, Qualitative Analysis of Fanno flow. In this lesson, we'll discuss what happens when friction is increased on either branch of the Fanno curve. We'll discuss choked+Fanno flow in more detail, and I'll show you how both the subsonic and supersonic branches have some strangeness. This will be a qualitative analysis, and we'll do a quantitative analysis with more equations in the next lesson. Here's our setup. We go from state 1 at x1 to state 2 at x2 through a constant area duct of length L, and we do have a friction force F friction acting by the wall on the fluid as sketched here, but no heat transfer. Let's review the Fanno curve, where I'll plot a TS diagram as usual, and we have our subsonic and supersonic branches with the critical or sonic conditions at this point of maximum entropy. And recall from the previous lesson, starting at 1, we can move only to the right, and this is true on either branch, because S must always increase due to irreversible friction. In this lesson, we'll look at which properties decrease and which increase in Fanno flow. So right away, we see that in the subsonic branch, temperature decreases as we keep increasing friction, and in the supersonic branch, temperature increases as we increase friction, both approaching the sonic or critical state as we discussed previously. So in the subsonic branch, T goes down, and in the supersonic branch, T goes up. And we're always talking about going from state 1 to state 2 downstream in the duct. Recall for Rayleigh flow, the curve looked more like this, and we had a strange region here where the temperature dropped. So temperature goes up in the subsonic region until it reaches a maximum and then drops. And I called this region the strange region or the strange zone because we're adding heat and temperature goes down. In Fanno flow, we have no such strange region, except that the entire subsonic branch is sort of strange, because if you think about it, we're adding friction, and yet the temperature goes down. So I'll write here, the whole subsonic branch is strange. Instead of friction heating up the flow, friction actually makes temperature go down. This is non-intuitive, but we have to think of our other variables in order to explain it. For example, Mach number goes up in the subsonic branch because we start at some subsonic Mach number like 0.2 or something, and we go towards Mach number 1 at the critical state. So Mach number increases. On the supersonic branch, we start at supersonic conditions and head towards 1. So for the supersonic branch, Mach number decreases. And I'll write here as m goes to 1 in either of these cases. Let's examine this using the energy equation, namely that T naught is CPT plus V squared over 2, which is a constant for Fanno flow. So in this subsonic branch, as T goes down, V must go up so that the sum of these two terms remains constant. And in the supersonic branch, we have the opposite effect. Temperature goes up, so speed V must go down. Let's also consider conservation of mass, where we had rho V equal constant. Therefore, rho behaves oppositely to V in Fanno flow. The same thing is true, by the way, for Rayleigh flow, since both of these are 1D flows with constant area. Thus, continuing our table, we already talked about T, M, and V, and now because of this opposite behavior, we add that rho must go down in the subsonic case, and rho must go up in the supersonic case, opposite of the behavior of V. What about pressure? Well, let's look at the ideal gas law. Since P equal rho RT, and R is a constant, P over rho T must be constant. And we'll think about this in the subsonic case. T goes down, and rho goes down, so the denominator gets smaller, but in order to keep this constant, pressure must also go down, therefore, and I'll add that to our table. The supersonic case is opposite, since we see that temperature and density go up. Therefore, P must also go up to satisfy this, and I'll add that to the table as well. This behavior is also strange because we have a long section of pipe, and you normally think that you have to push the flow through the pipe with pressure going down. But here we're saying that P goes up to the right as the flow goes to the right, even though we have friction on the walls. So the whole supersonic branch is strange. I call it supersonic strangeness.
Strange indeed. Sir, can you explain how pressure can rise even though there's friction down the pipe?
Okay, Boris, I'll try. But it's not unprecedented. Recall for incompressible diffusers, we had a similar effect where the flow enters to the left and exits to the right, so the speed goes down, but the pressure goes up. And beginning students of fluid mechanics have a hard time understanding how the flow can go from left to right without pushing the flow through, with the pressure actually going up.
Thank you, sir.
And I explained this phenomenon in a few of my other video lessons. I'll make this kind of a side comment, and I'll try to explain why we have this strangeness. We'll do so by considering our x momentum equation, which I rewrite here, which was our equation 3 in the previous lesson. Let's rearrange this as follows. P1 minus P2 plus ρ1 V1 V1 minus ρ2 V2 V2 equal F friction over A. But we know from conservation of mass that ρ2 V2 and ρ1 V1 are the same. So that grouping in either of these terms is a constant. So again, I'll rewrite and rearrange as some constant times V1 minus V2 plus P1 minus P2 equal F friction over A. Now we can examine these terms. For subsonic Fanno flow, recall from our table that V goes up, so this term must be negative. The term on the right is always positive because you can't have a negative friction force, and we've defined it in the proper direction. So what does that do with the pressure? Well, if this term is negative and this term is positive, this term must be positive. Therefore, P1 is greater than P2, or P goes down. On the supersonic branch, we know that V goes down, so this term is positive, and this term, of course, is still positive. Thus, the pressure term can be positive or negative. So how do we know which it is? Well, if V1 is much greater than V2, the V term, namely this term, dominates. Therefore, P1 minus P2 can be negative. But if V1 is not much greater than V2, then the pressure difference must be positive to keep this right-hand side positive. Well, the first case turns out to be the one that's correct. In other words, P1 minus P2 is negative, meaning that P1 is less than P2, or P goes up. Thus, the behavior for subsonic flow is opposite that of supersonic flow in terms of pressure. As a side note, on both branches, subsonic or supersonic, pressure goes down when speed goes up, and pressure goes up when V goes down, which is easy to remember because it's the same behavior as our beloved Bernoulli equation that we all know and love from undergraduate fluids. Finally, I provide here a qualitative summary of Fanno flow. I'll make a little table again of the property, the behavior in the subsonic branch, and that in the supersonic branch. Speed goes up in subsonic and down in supersonic, the same as Mach number in both cases. And we remember that because m must approach 1 as we go from 1 to 2, heading towards critical flow. Temperature goes down in the subsonic case and up in the supersonic case. Density follows the same pattern as temperature, down and up. And pressure also goes down subsonically and up supersonically. Notice here that temperature, density, and pressure, all three go down in subsonic and all three go up in supersonic. But they're opposite between the subsonic and supersonic branches. Specific entropy, on the other hand, goes up on either branch because these flows are irreversible due to friction. there is a property that remains constant, namely T0, which is constant for either branch. This is in fact the only property, other than H0, that remains constant in Fanno flow. What about stagnation pressure? Well, it goes down for both branches. I like to say that because of the friction, we lose some oomph in the flow, so P0 must decrease, which is exactly what I said across a shock. You can also put a dividing line here and notice that these properties all behave exactly oppositely between subsonic and supersonic branches, but these lower three here all behave the same. I'll also comment that this Fanno flow behavior is nearly the same as for Rayleigh flow with heat addition, except T0 goes up in both branches of Rayleigh flow, but P0 goes down, entropy goes up as we add heat. Speed and Mach number behave the same way in the two branches for Rayleigh and Fanno flow. But most of these other variables like density and pressure behave the same for both branches between Rayleigh and Fanno flow. Temperature is different though. In the subsonic branch, recall the strange zone in Rayleigh flow where T goes up, then down for a small region, the strange zone, in the subsonic branch of Rayleigh flow. But other than that, most of these properties behave the same. I'll also comment that this qualitative Fanno flow behavior is also similar to compressible, isentropic, and adiabatic converging duct flow, which we discussed in earlier lessons, namely, again looking at the two branches. For the subsonic case, with m less than 1, Mach number goes up and can choke at the exit plane. But if I copy and paste this for the supersonic case, where we start with m greater than 1, Mach number goes down, but still approaches sonic conditions. As you may recall for converging duct flow, in addition to m going up, V goes up, temperature goes down, density goes down, and pressure goes down, with exactly opposite behavior for the supersonic case, V down, T up, rho up, and P up. Again, these three behave consistently in both the supersonic and subsonic branches. In both cases, T0 is also constant, which is also the same as our Fanno flow. But there are differences. Entropy remains constant in converging duct flow, since this is isentropic adiabatic flow. And since we don't lose any oomph, stagnation pressure also remains constant. And as I said at the beginning of this lesson, this is just a qualitative analysis of Fanno flow. We'll do a quantitative analysis in the next lesson.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3. That's all there is to it.